yellow folly. I hope you are well rested. Even puppies need a nap after learning KMP. Algorithmic abilities are flowering. Heralding a new week. Welcome back.
Good morning, everyone, and lovely to see you all again. Today's historical figure on the screen is Barbara Liskov. She might be a little less known than Alan Turing or some of the ultra-famous figures. However, she made just as important contributions to the history of computer science. She was born in 1939 and was the 2008 Turing Award winner, currently a professor at MIT. So we're starting to get to a couple of important figures who are actually still around. And if you have a good reason, you can probably email her and maybe even get a response. So Barbara Liskov's big contributions to computer science were ideas around the fundamental nature of abstraction. In fact, she is largely responsible for the ideas that led to object-oriented programming, which is the name of a subject that many of you might take, but is also something much deeper around the way that we represent data, and we'll actually talk a bit more about that during today's lecture. One interesting fact about her life is that Princeton refused to let her in because she was a woman. They refused to let in a female mathematician into their PhD program, so instead she went to Stanford. And this is part of a long history in computer science of minoritized groups really being given a difficult run, being discriminated against persistently, and still to this day we are kind of struggling against those trends within the industry to try and balance it out and make it a fairer place for everyone. So along with her technical contributions, Barbara Liskov was instrumental in kind of beginning to even up the playing field again. Part of the interesting history of computer science is actually that in the part of history when computer science was seen as less intellectual work and more drudgery, back when women were computers, that was a time when minorities and women were encouraged to become computers. And of course, as it became higher status, while the world still was in the throes of a particularly misogynist era, then as the jobs became higher status, the jobs moved back towards men. And hopefully, as the arc of history bends more towards justice, hopefully we're going to see that balance a little more out again. So returning to our talk from last week about string pattern search, let's remotivate it again with a question that might be a bit more relevant to some of you. So let's go back to our algorithm, KMP, which was our string pattern search. But fundamentally, we want to understand, are the algorithms that we have developed powerful enough, efficient enough to let us search through a large body of text, such as the text in the Baillieu library? So you might ask, why am I trying to do this? Well, hopefully some of you are starting to write essays for your breadth subjects, or maybe even for a good computer science subject that gets you to dig a little into there, and you're looking for some historical references. Perhaps you're searching for where a quote appeared, or for text that pertains to a certain topic. And the library search engine is, of course, a place that you would go. Now, the library search engine is a smaller scale version of what we do every day when we go to Google search. But let's just try and confine the problem to something small for the time being, nice and tiny, the text in the Baillieu library. So we're going to start off, maybe let's give Christian a go. How many of you have heard of Fermi problems before? Okay, we've got one. A Fermi problem is this idea of trying to just, on the basis of reasonable A Fermi problem is this idea of just trying to make some reasonable assumptions to solve a big numerical question. So for example, how many window washers are there in Seattle is a famous interview question that Google used to use. So we're going to do a similar Fermi problem with Christian for figuring out how much text is there in the Baillieu library, and as a result, whether KMP is going to be an appropriate algorithm for us to use. So how many characters do you think there are in the Baillieu library?
Millions.
Millions?
Hundreds. Millions,
Hundreds?
yeah.
Millions?
Hundreds of millions, I don't know.
Okay, so let's start from a reasonable starting point. How many books do you think there are in the Baillieu?
Several thousand, maybe.
Several thousand books? Yeah. How many books do you think are on one shelf?
Maybe 100.
Okay, 100 books on one shelf. How many shelves are there in a single side of one stack?
Maybe 4 or 5.
4 or 5. Have you been into the library?
I haven't been in, just in the study areas. Not
Okay,
as
so
much,
it's you're probably underestimating a little.
Yeah.
Let's say there are 10 rows on one side,
Yep.
and let's say 100 books. It's probably an severe undercount, but
Yeah.
let's go with it. So that is 1,000 books on one side of one row of shelving.
Yeah, okay.
We've got 2 sides of the shelving.
Yeah.
So that's 2,000 books
2,000, yeah.
on the single rack of shelving. How many racks of shelving do you think there are in the entire Baillieu building?
Oh, probably over 100. A lot, a few.
Over 100? So maybe let's go with 1,000.
1,000, yeah.
Okay, so we have 2,000 books
Yeah.
per row, per shelf,
Yeah.
and 1,000 shelves. What do we get?
1,000, 2,000, 200,000, 2 million.
2 million?
Yeah.
Okay, and now how many words are there in a book?
Depends the size of the book, I guess, yeah.
Your average, we're looking for a guess at order of magnitude for the Baillieu library.
Pages. I've got no idea, to be honest. Yeah.
So let's go with 50,000 words in a small book and probably 100,000 words in a big book. And are there big books or small books in the Baillieu typically? This is a scholarly library.
Yeah, probably big. Yeah.
Probably big books.
Yeah.
So let's go with 100,000 as a small number.
Yeah.
And how many letters do you think there are on average in a word? Just has to be a reasonable estimate.
5.
5 to 10?
Yeah.
So let's just peg it at 10.
Yep.
So we have 100,000 words per book and 10 letters per word, including punctuation, all of that. So that gives us
10 million.
100,000 times 100,000 words times 10.
A million. 10 million.
100,000 times 10. It just gives us 1 million.
Yeah. Okay.
Right, 1 million.
course, yeah,
So we've got 1 million characters per book. And then how many books did we say we had?
2 million.
So we had 2 million. So 1 million by 2 million
It's a lot, yeah.
gives us roughly, you know what a million by a million is?
Billion.
10 to the power of 12, which is, anyone know? 10 to the power of 12 is? A trillion, yeah. So we have roughly order of magnitude 10 to the 12 characters per book. Now thank you very much, Christian. I know that was a bit of work for you. Let's see how it goes when we actually get the data for us. Keep the microphone for the minute. We'll keep one up there to pass back. Okay, so this is a figure I took from 2012, a table I took from a 2012 report on the Baillieu library. And these were some of the numbers I got. So the library contains approximately 78 kilometers of shelving on approximately 78 kilometers of actual shelved material on 101 kilometers of available shelving. So that's a hell of a lot with approximately a 77% utilization rate if you look at that. So let's go to some numbers that I crunched for us earlier. 100 pages is approximately 10 millimeters thick. So we can actually take the length, the distance of the consumed shelving and figure out how many words per inch or per millimeter of shelving. 300 words per page, 5 characters per word, 15 characters for every 300 words. That gives us 150,000 characters in every 10 millimeters of shelving. We had, how many kilometers was it? 78 kilometers of shelving. That gives us about 10 to the 12 characters in the Baillieu. Approximately. It might be a 10 to the 11, might be 10 to the 12, But using this Fermi calculation, we should have a reasonable kind of guess for how many characters in the Baillieu library. And these kinds of problems actually do get tested in job interviews. So I would recommend having a practice with a couple of these at some point during your undergraduate career. It's also a good way to check your answers to something. If you know roughly the order of magnitude that your answer is meant to be, and if this number was 10 to the 18 or 10 to the 2, we'd know that we'd made some incorrect assumption or we'd done something wrong in our calculation. So this is a very powerful tool, not just for computer science, but generally speaking. So how long for a KMP search on this text? So here you'd actually need some numbers that are a little less accessible. So I ran this benchmark earlier today, and you'll see in slides from past years, this number is a little different depending on the specific bit of code I chose to do this on, but it was approximately 0.3 seconds for a pattern search of a small pattern, 5 to 10 characters, in a pattern length of 100 million characters on an implementation I actually tried just this morning. So if we crunch those numbers, so 100 million characters, we're actually looking for how many times does 100 million fit into a trillion to do one search on the entire Baillieu library, which gives us about 50 minutes for a single search, using up an entire computer's processing power, or at least one core on an entire modern computer. So what do you think, Christian? Is this going to be appropriate for us to do our search?
Probably not.
Okay, so what are some options that we have to improve on this?
Not too sure, to be honest.
So say a bit louder?
Not too sure.
Okay, so how many cores are in one of these computers? Do you have a guess?
10 to 12.
Yeah, on my super expensive Mac, I've got like 12 cores. On an ordinary computer, an ordinary laptop, you might have 2 to 4 to 8 cores maybe. So we could do like 12 searches simultaneously on my laptop, and then after an hour would get the results from the entire Baillieu. But that's still probably not going to cut it. How many searches do you think are done on the Baillieu Library website every day? Just order of magnitude guess. Same kind of principle?
20,000.
So we have like 50,000 people in the university. You probably do a search, I don't know, once every couple days, optimistically, assuming that you guys are using the library. Garv says that's very, very optimistic. But we probably have at least, at the very minimum, on the order of hundreds of searches a day. But really, most of the active researchers are going to be using this a little more than once every few months, as Garv might be using it. And if we're using it to that extent, a few hundred searches every day, well, we're not going to be able to do it even with dedicating an entire computer just to the searches. And essentially what this means for KMP, which is a little surprising, is that O of n is not going to be fast enough. Now, that's a little shocking. O of n is great. We've been working all our time with our sorting algorithms that are like n log n, or worst case n squared. This is a little unfortunate for us because it's often pretty hard to do better than O of n. So I'm going to take you back to the very first lecture in semester where I showed this figure and talked about space and time trade-offs. So this was the idea, for those of you that can remember all the way back 7 weeks ago, that sometimes you might be able to build an algorithm that allows you to speed up how much work you do at a given time by doing some pre-computation and saving a lot of memory, saving up a lot of memory earlier on, filling it with something that gives you assistance in performing your later computation. So if we can figure out a cleverer way to represent our data and store it in a computer's memory and store that ahead of time, maybe we can make our searches more efficient. And that is going to be part of the big idea for the first half of today. So with that, let's get Claire Zhao up to the front. And I need your help for a minute. Okay, so we've had one lecture already with the white pages, and now Claire is going to help us out with the yellow pages. Have you ever used one of these before?
Oh, not actually.
That's okay. We're all going to discover what the world looked like prior to 2010. So I'm going to hand it to you, and you can flip through the first couple of pages. Just open it up somewhere in the first half, and just flip through and see how it's organized. Flip through a couple pages. Okay, you think you got a sense of it? Yeah. Okay, tell me what's going on.
So they have listed a lot of things categorized by their functions.
So hold the microphone a little closer so everyone can hear you.
Oh, okay. So they got a lot of things that has been categorized by their functions and their usage, I guess.
So they're all businesses, right? That's what we're looking for, and we were aiming to find the phone number of a given business. So if I wanted to find a camera business, what would I do?
You can I look at it again?
Yeah, you can look at it.
Oh, they have alphabet at the top of the page, so we can just flip to C,
And
or P for photograph.
probably, I think C. Take a look.
C?
See if you can find it. See if you can find a camera business.
I found camping, but not camera.
What did you find? Okay, we found cake shops and cafes. Okay, so let's go with a cake shop. Okay, let's say we were looking for cakes instead of cameras. Maybe P is photography.
Yeah.
So how did you go about finding that?
Yeah, just go through by alphabetic order.
By alphabetical? And is there a faster way maybe of doing that rather than flipping through pages? Let's take a look at the very start of the yellow pages. I think you've probably found it. Yes, what have you found here?
There are indexes.
Okay, an index? Explain to me what that is. I don't know.
So they have gathered all the elements we need, and they put into pages, and then we can find it accordingly.
Does it have all the elements in the entire yellow pages at the start? What does it have?
Yeah, just the name.
The name of the...
The name of the business.
Are these business names?
Oh.
What are these?
Or the type of things that we want to find.
Yeah, they're categories. Give us a few examples.
For example, for Aboriginal art and crafts, and
What's a different category? Just pick one.
audiologist.
Yeah. So at the start, we have this mapping between, it's going to be a little hard to put up. We'll skip that for the time being. At the start, we have this mapping between the business type and the page on which that business type is found. And then what we can do, how do we use the index?
We can just look at the pages that is listed on, and then
if I wanted to find a cake shop using the index, what would I do?
You can go to letter C and find cake shop.
C in the whole thing, or C in the...
C in the index.
C in the index, okay. And then what do we do then?
We look at A followed by the C. Yeah, and look at the pages that it's listed.
So once we've found cake shop, we look in our index and it tells us where to jump somewhere in our other data structure. So we have our big array that has all the businesses, and then we have an index which tells us how to jump in midway through our other data structure, through our array, and tells us where is the index at which all the cake shops start. Thank you very much, Claire.
Thank you.
It's probably been a while since any of you have used one of these. Can we have a round of applause? Come on. So this is essentially this whole idea of space trade-offs for improving efficiency is what we've done here. Someone has gone through, and not only have they organized things alphabetically, but they've created a second data structure that uses up some extra space. It uses up, I don't know, it uses up another 5 pages in the book, but those 5 pages in the book allow us to quickly jump through the rest of the other pages to find elements that we might need. So no longer do you have to go through the entire thing trying to do like a binary search, figuring out where the letter C might be. Instead, you go right to the start, to that index data structure, and allows you to jump somewhere else in the data structure. So an index is this idea of storing data by a keyword or some other shortened listing that allows you to more quickly navigate through the second data structure to which it refers. So there are numerous examples of this in real life. We use indices not just on a computer, but in all kinds of places. So if you open a filing cabinet, you might see those little stickers pointing out that have the letter or the category of things stored in the filing cabinet. We use indices, like if you've ever seen a lawyer who has a big folder of briefs, they've got the sticky tabs that come out showing you where to jump. All of these are examples of indices. And books, also if you get like a scholarly book, you'll often find an index at the back of the book that allows you to quickly find a word in a list of words. Now, this is all well and good when we know ahead of time, say, all the categories of businesses that we want to look for. But one of the challenges that we've got in extending this to something like KMP is that we might want to find an arbitrary pattern within a given string. So this makes our challenge a little bit harder. And we'll talk a bit more about that in a second. So let's say I've got my index at the start. Algorithmically, what is a fast way of navigating to where we want in the index? Assuming it's a string-based index.
And assuming that the index are you looking for a substring in one of the indexes, or are you
Let's
looking
just
for
say
the
we're looking
entire
for a
index?
particular value in it.
Then probably just binary search.
Binary search, okay. So we've got binary search that works so long as our index is sorted. And this idea is going to allow us to do something efficient when we think back to find repeats from the very first lecture again. So today is kind of throwback lecture day. So let's go back to find repeats, and you'll remember that we were looking for a repeated string inside a larger pattern. So let's go to our example string that you might have seen last lecture of she sells shells. I'm not going to put the she sells seashells, that's going to take way too much space. But let's go back to this structure and create our suffix array. So the way we started with this was to put all the suffixes in the array in order. So in index 0, we have the full string. Then in index 1, we've cut off the first letter and just have that suffix. In index 2, we have the suffix from everything from position 2 onwards, and so on and so forth. And then our trick was to put all of these strings into sorted order. So now we have the $, which was our special character at the top, and then our hashes, another special character, we'll put them next, and then we'll go alphabetically. So E, H, L, S, the starting letters of each of those patterns. Now, even though we've resorted things, these new sorted items are probably still contained in a data structure themselves. Just because we've resorted the array doesn't mean that the original array indices don't exist, so I'm going to put them, that the new array indices don't exist, so I'm just going to put those up there listing them as well. So now we'll have our array, our new sorted suffix array T, but we'll also have an array S. And what S is it is a mapping that tells us where it tells us the original index of each of the shuffled items. So let's go back slightly. And here we can see that 16 has now been, the item that was formerly at position 16 has now been moved to position 0. And so our supplementary array S is just telling us what that mapping is. So now it makes it very easy for us to tell if a given pattern is in our data structure. How do we do this, Darcy?
Binary search again?
Yep, binary search. So is ls in our target string? We'll do binary search. So binary search can work as follows, assuming that we've set things up this way. So in our very first step, divide the array into two. So pick the halfway point, and the halfway point will take us to LLS, and then which half we want to keep. We want to keep the LLS half, then divide that into two again. Which half do we want to keep? Well, halfway takes us to LS, and we've found LS very, very efficiently without having to do a large number of steps to figure out if this substring was in there. Now, we'll pause and give Tim a chance to ask a question.
So in that case, the pattern was just ls, which happened to be a full suffix, right? But in some cases, maybe like the suffix would be lst, and we only want ls. This would still work for that, right?
Well, you could just compare up to the first n characters.
Yeah.
But if you're looking for a partial suffix, the process is still going to be the same. Because you've got an array that contains all possible suffixes, you've got an efficient way to look up and to index into it using, actually, you don't have an efficient way to look up. You've got an efficient way to search through it using binary search. And then you just say, okay, if we were looking for, let's look for LSSH with a space between, which we've here put the hash mark, the pound symbol in, just to remind us that there's a space because it's harder to see there. So if we were looking for LSH, then what we would have done is we would have thrown out the top half. We would have gotten to LS pound symbol shells $sign. And then when we start comparing with that, we just compare the first 1, 2, 3, 4 characters, and then we've found a match for the complete pattern without having to go through the complete target element in that suffix array. So it still works perfectly fine. And this is great. Now we've used an auxiliary data structure to avoid the issue that we were having with KMP. KMP is really efficient for when you're not willing to do that pre-computation work ahead of time to store a large suffix array. Now, in order to do this fast pattern, we had to store this very large suffix table, but it makes things very efficient for us. We do the suffix array construction once only, and then every time we want to search for a pattern, we've already got that suffix array stored in memory, and we can reuse it again and again, and then just do our binary search for whatever the new pattern happens to be. So let's do our time efficiency calculation. How long does suffix array construction take? Let's leave that for a minute. And then how long does binary search take? Tim, you've still got the microphone.
Linear time. Oh, sorry, which binary search?
Binary search.
And log 2n?
Log n.
Log n.
Log 2n, but we can ignore the 2. And just, we always throw out the 2 in computer science because the base doesn't matter in big O notation. So let's say m is the length of the pattern, and we have to go through we have to go through log n steps of division to get to where we only have one element left to check. So that gives us log n times that we possibly split it in 2. But this is string pattern search. This is string binary search and not just plain binary search. So when we get to a given element, we might have to check a certain number of letters in. So we just are going to multiply that by n. So that leaves us with the other half, which was the suffix array construction. And here the analysis gets really, really difficult to the point where I actually don't understand a lot of the details of suffix array construction. But we can start with a simple algorithm for suffix array construction and then see how deep into the weeds we can go. So method 0, which we talked about in lecture 1, add n strings, each of maximum length n into the array, and then just sort them. Now, of course, each of the strings is maximum length n because... Tim, do you want to pass it in front of you? So how do we know that the strings are of maximum length n and that there are n of them?
This is when we're constructing the suffix, right?
Yeah.
Well, isn't n the length of the entire character array?
So n is the length of the entire initial string. So she sells shells.
Yeah.
And then from that we know...
Well, it can't really be any longer, and each one kind of decreases, so it's never longer than n.
Yeah, the rules for a suffix is that it is, you cut off a given number of letters from the start, and given that we had n letters to begin with, the longest that any of those strings is going to be n, and we know that there are only n possible suffixes because you can only cut off n letters before you get to no letters left. So we know that there are n strings of maximum length n, and to sort n strings of maximum length n is n log n times n, because that's the length of the string, and plus n just for iterating through it once. And that's going to give us big O of n squared log n, character comparisons on average. And it's important to say character comparisons here because we're not, when you think of comparing two strings with each other, which is how all the sorting comparison-based sorts work, is by comparing two elements. Comparing two integers only takes one step, but comparing two strings takes longer because you, in the worst case, will have to check each of the letters to find that they mismatch only at the last place. So that's how we get n squared log n. Now, it's not particularly good. Log n is generally going to be larger than 1, so this is bigger than n squared time. Not great. Okay, we can do so we could do something slightly cleverer than that. Add n strings into the array, and then use a slightly better way to compare and sort the suffixes. We can do log n sorts, and there are some fancy ways of sorting strings in particular that we can use that will give us n log squared n character comparisons average. So this changes one of those factors of n to log n. Looks a little better, but how do we actually do better suffix sorting? So let's go back to our picture that we had before. And we see that unlike a generic sort for items of arbitrary length and arbitrary composition, we know some things about our elements of our array. So this one's a little more abstract. Maybe let's give the microphone to Jabu is your name, right? Let's pass it down there.
Yeah.
Okay, so what do we know about strings in C?
They're just an array as well.
Okay, they're an array. What else do we know about them? What do we know about each of the elements of the array?
It's just a number.
It's a number. What else do we know about the number?
It's between 0 and 127.
For pure ASCII, between 0 and 127. And if we're just talking about alphanumeric characters, let's say, and they're all uppercase or lowercase, let's say we're doing case-insensitive search.
Well, it should be around 65 to or 90 if you treat it as uppercase.
So we have a very small number of possible values, which means that if we're sorting things by a given letter, there are only a certain number of piles that we possibly need to sort things into. And one could imagine, take this intuition all the way to the extreme and just say, okay, put everything in a pile that are based on its first letter. So let's say there are only letters allowed for example purposes, and the first letter is A, put that into a pile for all the things that start with A, and then worry about how to sort the second letter. If it starts with a D, put it into the pile of all the things that start with the letter D. And we know that in the worst case, if we're only dealing with letters, how many piles will we have maximum?
26.
It's 26 piles, and each of those piles will be divided into a maximum of
26 more piles?
Yeah, 26 more piles, and we can figure out how many piles we will have at maximum if we have a maximum length on our pattern that's reasonable. So if we have 26 piles and each of those piles turn into 26, and each of those piles turn into 26, etc., and we do that 10 times, we get
26 to the power of 10.
Okay, but that's a little too big, right? So instead of dividing it into 26 piles, we could divide it into 2 piles, but that's really just what Quicksort was doing before, right? We haven't really gained any advantage. So we could probably go somewhere in between these two and use something that we call ternary quicksort. And this is a particular type of ternary quicksort because it's a string sort. This algorithm is due to, remember who it's due to, Bentley and McIlroy. So this is Bentley-McIlroy ternary quicksort, and it's a way of essentially, oh, I'm one slide too early. This is Bentley-McIlroy ternary quicksort, and it is essentially capitalizes on this idea that we know that there are a limited number of letters. So here what we're relying on is that common prefixes are going to allow us to speed up some of the computation. So we have a question back there.
So my question is, what if we're doing, say, Chinese, for instance, where we have thousands of characters?
So then the specific bounds on this are going to change. It's going to be less efficient when you have a much larger alphabet size, but the algorithm still works.
But the thing is, Chinese doesn't use an alphabet per se.
It uses characters.
Yeah, we have pinyin. There is pinyin, but the thing is, it's mostly characters. So
Yeah,
how
so
does it work in that case?
Look, you could do this with words. The larger, we have what's called an alphabet, and an alphabet doesn't literally refer to an alphabet in the Western sense of like A, B, C, D. It refers to all possible symbols that one could have. And the larger your alphabet becomes, the worse this algorithm is going to be at handling that problem. However, for a bounded alphabet size, you still can bound the runtime of the algorithm, but the actual performance, like the number that you get out with a bounded alphabet size, is going to be worse if your alphabet is really, really large. So if you're in a language that doesn't have a standard alphabet of like 26 characters, but instead the only way to represent things is by using a specific symbol for each word, then this technique is not actually going to get you performance benefits.
Okay.
But for other languages, there are going to be different techniques and different data structures that one can use to speed up search. It's just probably outside the bounds of today's discussion how to do this for different given languages. So our ternary quicksort idea relies on pretty much the same concept, the same conceptual basis as Quicksort, but adds this idea of instead of just dividing things into 2 piles, let's divide things into 3 piles, still pick a pivot, and we're going to have 1 pile is all the strings that begin with the same letter as the pivot, 1 pile for everything that begins with a letter less than the pivot, and 1 pile for everything that begins with a letter greater than the pivot. So rather than doing 1 pile for every single letter, we're kind of splitting the difference between the two. So what we're going to do looks roughly as follows. So pick a pivot, and just for convenience's sake, for the time being, we're going to again pick the very first element as our pivot. Now do the partition, put everything whose first letter is prior to the pivot lexicographically into the top pile, put everything in the middle with where the first letter is the same as the pivot, and then everything at the bottom where the first letter starts after the pivot. And now rinse and repeat, recurse. So for everything that was in the same as the pivot pile, we now know the first letter is irrelevant for determining their subordering within that middle pile. So for them, rerun the algorithm from scratch. And for the other 2 piles, so for them, we're going to have to rerun the algorithm from scratch. And for the other 2 piles, we're going to have to similarly choose a new pivot. So let's look just at the middle pile for the time being. And for the middle pile, we are going to choose seashells as our new pivot. Seashells, we've already looked at the letter S, so there's no point comparing the rest of its pile with the letter S. So we've saved some work there. And instead, we now look at everything relative to its second letter. We now look at all the words in that pile. Let me say that one more time. We now look at the second letter of all the words in that pile and compare them to the second letter in the word seashells, the letter E. So everything whose second letter is before E goes in the top pile. Every word whose second letter is the same as seashells goes in the middle pile. And everything whose second letter is after E in the alphabet goes in the last pile. And then we recurse. Let's do this again. Okay, top pile over there. We are now looking at the third letter in seashells, which is A, and do our partition again. So this is going to allow us to do an n log n search for adding our strings into our suffix array here. Tim, where is Jabu has the microphone?
So, but this won't fully alphabetize our array, right? Because since we're only looking at each letter once, we're putting it into, like, suppose we're looking at the S, right? Then we're putting everything into, or like, buckets of if it's before S, after S, or is S. But then when we, like, are in that bucket, we're skipping all the way to the next letter. Like, we're not going and alphabetizing it, like, it's not going to be fully alphabetized by the first letter by the time that we've moved on to the second letter. Is that correct? Or
no. If you look here, it's we know that the things on the top part are all before S and the things in the bottom part are all after S, and we're going to recurse on them later as well. I just haven't shown that part of the process. So this process that I've showed here, if we keep following it along for the middle section, will ensure a total ordering of the middle section, a complete alphabetization of the middle. And then what we do is we just repeat the process on the top half of all the things that were before us and on the bottom half.
what I mean is, doesn't that mean that we're actually looking at the letter more than once? Because okay, let's take in the first iteration here, we're looking at the S in she, and then we're just taking the whole array, organizing it into 3 buckets based off of whether the first letter is before, middle, or after. But then when we recurse to looking at the B in by to sort that subarray, that's looking at, we've already looked at the B in by because we had to sort it into that bucket in the first place. So isn't it technically the case that we are actually looking at each letter more than once?
That's where the size of the alphabet becomes important. Because you know if there are only 26 letters in the alphabet, then there are only 26 possible times that you could have stuffed that up. So for a letter that's in the middle pile, the one that's let me say that again. When you advance the depth by 1, so we've now, for the S section, all of those letters have been advanced by 1. So we know at least for that section, we've only looked at the first letter once for the pivot. Now, for the other elements, there are only 26 letters, and so there are only 26 possible times that you could have actually messed that up. So as much as you are correct that not every word in the entire thing will have its first letter looked at once, you can only do an incorrect, you can only look at that first letter a maximum of k times, where k is the number of characters in your alphabet. That make sense? And that is essentially where the overall benefit is coming from. If we didn't have that guarantee, if that could truly be any value, any symbol, then we lose that speed up. And what is happening here behind the scenes is that we are effectively using our data structure to cache, to store a bit of extra information about all the things that we've sorted. Namely, we are saving the work for every time we advance into the string deep. So we have our 3 different quicksorts. We have one quicksort that looks at everything up until the first equal marker. We have one quicksort that looks at everything in that middle section, but advances the depth parameter by 1, which tells us how deep in the string to look. And then one quicksort that looks everything in the latter half. We're not going to step through this code in detail. You're welcome to do it on your own time. But structurally, it's near identical to regular quicksort. And we'll stop for a couple questions. Garv, Tim, you've got the... So moving on a little, let's actually, instead of, I'm not going to step through the code for this one. This is a pre-prepared example. But we can see quite how fast it is and give it a run. So here, if I have set things up correctly, there we go. And this is a fairly well-optimized version of Ternary Quicksort. Oh, Alex has got a question.
Sorry, I just was wondering whether the pivot selection also...
Yes.
Yeah.
Pivot selection is still going to matter. It will give you different real-world performance.
Okay.
But this code is available for you to download, and you can change the pivot selection and experiment and report back to us what you find.
Right.
Feel free to do an ed post. I'd actually be curious to see.
Okay, thank you.
No worries. Okay, so here I have some pretty complicated string sort code that I've actually taken from John Bentley, who was not only the author of the algorithm itself, but who also wrote a well-known textbook and it was a researcher as well, and also wrote the book Programming Pearls, which I referenced early in semester as a good way to learn a bunch of tricks to make your code very efficient and learn to think about algorithms in a better way. So I'm repeating my book recommendation. We're doing a fair bit of John Bentley stuff in class, so if you want to learn directly from the master, go check out that book. So let's go to lecture 7. I'm going to remember my correct lecture this time and compile stringsort.c. And now what I'm going to do is I'm going to use some commands to extract the first 500 characters from my Moby Dick book. So here I have the text of Moby Dick, and I'm going to use a command called head, which allows me to extract the first n characters from a given file, and here I'm going to extract the first 500 characters from Moby Dick and see how quickly this runs. Now, one other feature of what I'm doing on the command line here is I'm using this pipe symbol. So if you look at the backslash on your keyboard, if you hold down Shift, you'll get that pipe character. And the pipe does more or less what it says it does on the tin. It connects two different programs together. So in this case, I am taking whatever the output is from the head command, which is going to, oh, I missed something here. I have to give it a file. That head command is going to take the first 500 characters from Moby Alpha and then pipe it so that instead of requesting input from the user, string sort is going to just take whatever comes out the other end of the pipe and feed it in. So I'm going to run it, creating copies for testing. So normal quicksort took 0.01 of a second to do this. The built-in Qsort in the C library, which we'll talk about probably next week, which is a more optimized sorting algorithm, but it's generic, took a little less time, so that's 0.007, but still roughly same order of magnitude. And then my highly optimized ternary quicksort took 0.006, so beating that a bit faster again. However, if you look at the number of character comparisons that were being done, there is an order of magnitude difference there, which might indicate that if I wrote my program to handle larger inputs, I might see even more benefit. However, if we look up and see how my ternary quicksort was working, you can see that it was actually storing a fairly large amount in memory. And so I've got this trade-off that's going on when I'm trying to use this idea of storing larger intermediate data structures for an algorithm that might actually put a real cap on which algorithm I end up using. So this table has lots and lots and lots of entries, and eventually it's going to become intractable to store that in memory even while I'm just running the algorithm. But you can see my partial suffix array. So let's just do a search in here, there, and you can see that we got up to character roughly sorry, my n was doing 500 lines, not 500 characters. I would have had to give it a different flag to do up to 500 characters. So it's got up to the 500th line here. So there are a few reasons why my ternary quicksort worked. Reason number one was that it allowed us to avoid repeated work by not recomparing prefixes that we already knew to be in common. So with our S, once we already knew that the S was in common in the entire group, we didn't go back to look at that S again. There was another reason why it worked that we also discussed, and that's that there was a limited alphabet size so that the expected number of times that would save work was actually high. So it's these two facts together. A limited alphabet size means that we're going to have a lot of repeated prefixes, and a lot of repeated prefixes means that we're going to be able to take advantage of our algorithm that is structured to avoid that repeated work. So it's thinking about what your data looks like that allows you to get the advantage of these speed-ups. Now, we only got up to method 1 so far, but indeed there is method X. And there are lots of method X's, and they're all going to work in slightly different combinations of computer memory efficiency and time efficiency. But we do know that for a fixed size, for a limited size alphabet, we can actually do suffix array construction in O of n character comparisons. These algorithms are quite complicated. And in fact, a lot of people are still publishing research on the bounds for suffix construction under different scenarios, suffix array construction under different scenarios. And in fact, until a couple of years ago, Professor Andrew Turpin at the University of Melbourne was one of these people that was working on this problem. And indeed, if you look on the Wikipedia page of suffix arrays, you can see his name there. He had this really nice paper from 2007, which is a little out of date now. And I don't just mean that because 2007 was a while ago. The field has advanced since then. But he wrote one of the great surveys on suffix array construction algorithms. However, in 2016, there was this great advance by Uwe Bayer on linear time suffix sorting that really pushed forward the state of the art. However, Andrew Turpin is not the only member of Melbourne University staff to have studied this problem. And indeed, in not every class on algorithms in the world, you will find us obsessed with suffix arrays. The reason is probably because we developed some of these algorithms here. And indeed, you might see this other name if you go into the history of suffix arrays, Alistair Moffat, who is, of course, the professor who teaches Foundations of Algorithms the other semester, the author of our textbook, and the author of many of the code examples, most of the code examples that we use, was one of the other key figures in the recent development of suffix array algorithms. And so this paper was about figuring out how to reduce the space requirements for suffix array construction. Now, this paper is still from 2009, so we did 2007, 2009, 2016. And one thing you might be feeling in this class is, okay, I'm learning about a whole bunch of algorithms that other people have already created. And once I'm done with this class, then I kind of know the algorithms that there are, and all I have to do is pick the right one. I have some bad news for you. Unfortunately, we are not done creating algorithms, and we are not even done analyzing these algorithms that seem like they appear in a first-year class. So this is probably like foundational and settled knowledge. Oh, my dear sweet children. Here's a 2016 paper that develops things further. And this lists all the advances up till 2016 for different space-time combinations, depending on how much storage space you needed and how much time you needed. But there are still improvements still happening for parallelized constructions, faster implementations, so figuring out implementations that actually run faster on real computers, not just in a given time complexity, and then very large suffix array algorithms. So we were talking about searching through text the size of the Bailey library. My computer could only handle about 500 lines of text in a suffix array. And so we're going to need better algorithms that work for very large suffix arrays. So going back a whole bunch of slides to when we started talking about the time efficiency of suffix array pattern search, we can now substitute in our suffix array construction into here. We have O of n for our normal strings and of a bounded alphabet size. And we have search many times for m log n, where m is the length of the pattern. And overall worst case, what does this get us? Which of these two is bigger, m log n or O of n? What's bigger, log n or n? N is bigger, right? No matter how large m is, as long as it's fixed size, O of n is going to be the bigger one. So the lesson is use an algorithm many times. If we're going to be repeating search over and over and over, then it's better off to not repeat work and maybe store the work that we're going to repeatedly do by doing some upfront work, storing the results of that, and then reusing that work later on. So that is going to be a lesson that we will return to a number of times, and I've got hopefully a fun trick programming interview lecture planned for you where I'll show you how to optimize the hell out of a question that one particular tech company always uses in their interviews. So you'll be able to ace that interview. Okay, so that's our problem of string pattern search. But let's move a little beyond that. That maybe helps us solve a little bit or gain some insight into the Bailey library searching problem. But really, when we search on the library webpage, we want to do a bit more than just find the word itself, find which document it appears in. We often want to also figure out the context behind that appears alongside a key phrase. So here's an example of this that you use every single day. Any Lord of the Rings fans? And you'll see here, Google hasn't just presented us with the name of the document in which the phrase shortcut to mushrooms appears. It also provides some context, tells us some of the words that appear on a given website right next to the phrase a shortcut to mushrooms. So shortcut to mushrooms is the 4th chapter in the 1st book of the Fellowship of the Ring. A shortcut to mushrooms is the 12th soundtrack for the Lord of the Rings, the Fellowship of the Ring, credible PC game bundle. I haven't listened to that, but someone can tell me if mushrooms sound as good as they taste. So we now have a new problem that we want our search to do more than just tell us exactly where the phrase can be found. We want it to be able to return for us efficiently the words that are stored in that place as well, without having to go and grab the entire document in which it appears. So what are some options, some ways that we could think about doing this? Not Tim, because we've heard from you a bunch. We've heard from Darcy. G, you ready to answer a question already?
Asking me?
Yeah. Okay, Alex, let's pass the microphone back. Unfortunately, you caught my eye when you walked in. We don't want Google to have to re-download the web page every time we do a search. We want it to just look at the phrase we typed in and tell us what words appeared next to that word. That makes our search experience much faster because Google isn't re-downloading each of these web pages to tell us the context of the search phrase. So we know the user is going to search for a shortcut to mushrooms, but later on, we're going to want to provide some of the context. Right. So what we do is along with, when we're building our index, we're just going to save part of the context along with it. It's that simple.
Okay.
So give me a second. So our first option here is just to store the context along with the words that we're going to build into our index. So for every item in the index, fetch and store, when you're building your index, the words that appear next to it. So when let's say I am creating my index and I've just read in the sentence, she sells seashells by the seashore, and I know that the user is going to be doing single word searches. So let's say that they search for the word cells. Then when we put the word cells into our index, attach to it in some way, figure out how we're going to store that, the words seashells and she. So we could have a second array for all the words that appear in context before, and a third array for all the words that appear in context after, and just make sure that they're all in the right order, so that when we have an index for where it appeared in the, when we have an index for where it appeared in the index, that we can use the same index for the before context array and the after context array. So that's one way of doing it. The other thing that we can do, and that we do typically do, is store all the places where a given keyword occurs. Now, this is known as an inverted index, but is also would be actually quite familiar to any of you who've flipped through, say, an encyclopedia index before. So here's the back of an encyclopedia index at looking under the letter P around the word Portugal. So here we have, for the word Portugal, you can see there are a whole bunch of contexts in which the word Portugal appeared. And for each of those contexts, we list an index of where that particular context occurred. So rather than just going to all the different places where Portugal appeared and having a context listing for each of those, let me say that again. So rather than having a single listing for each time the word Portugal appears, we have one listing for Portugal, and then under it, we have a sub-listing for each of the contexts. So Portugal and Brazil, Portugal and Columbus, Portugal and Jews, Portugal and New World, etc., etc. And I will provide an example, a code example of running one of these inverted indices later for you to experiment with. So this takes us to the end of our discussion on string sorting. We can sort in linear time in the end, but we are going to have structure to leverage. So this was our suffix array that we could construct in O of n, and we were able to effectively do O of n pre-computation work to make this really efficient way to do our sorting and searching, but it's going to require some serious structure in the data that we know, such that we can use some tricks. So remember, we knew some things about the size of the alphabet that we were dealing with, and we also knew, what was the other thing we knew? Tim? So we knew that we were able to save repeated work for the repeated, we were able to anticipate that there would be repeated work that we could save for later. And now, one more thing before I'll take questions. And this is reflective of something we know about the real world. The real world has structure. When you're building an algorithm, you generally know at least something about the type of data that your algorithm is going to run on. And because of this, we can build algorithms that leverage the facts that we know about the data that's going to come into our application. So rather than just saying, okay, well, we think the theoretical best possible bound that we can get for generic sort is n log n. Take it a step further and say, well, I know that I'm going to be searching on strings, and I know that my strings are going to have a fixed alphabet, and I know that I'm going to be doing multiple searches, and so with all of that information together, that n log n generic bound is not going to be relevant for me, not the least to mention for which, because n log n is not, doesn't take into the fact that we have to search through the characters in the string, so it would be n squared log n or nm log n. But instead, we can leverage the fact that we know this extra information to gain substantial algorithmic speedups. And the big point here is if we combine data structures with well-designed algorithms that leverage those data structures, that is what actually allows us to get the speed up. And with that, we'll take some questions before moving to a break.
Just to clarify, so the OFN construction algorithm was the one that we didn't actually know, that was just like theoretically taken that we had OFN, and the one that we did explore was the ternary quicksort, which was
Ternary quicksort gave us n log n, yeah.
Okay, so the OFN, we just take it as given that we can get it that good.
Yes, you can, I'm happy to post online the details of it. Some of those algorithms get really tricky.
Okay.
I believe the competitive programming wiki might have a walkthrough that's somewhat approachable for one of the O of n construction algorithms.
Thank you.
They've also got a better n log n construction algorithm, so check out that wiki. Okay, let's go back there, and then while we're, Gaurav, pass it to Tim. Pass your old microphone to Tim, and then, yeah, go for it.
Right, so building off the previous question that I asked, because obviously we mentioned that this works because we know that the alphabet must be finite. Because obviously the thing is, between say finite alphabet for say the English and say Chinese, there has to be a limit where say eventually there must be a limit so eventually when it becomes the benefits just decline. So let's say instead we're working with say something as Japanese where we have a syllabary, for instance. Where's the limit for the size of the alphabet?
That's an empirical question, and that's going to start depending on particular parameters, like what is the actual pattern length that you're searching for, what is the actual size of the body of like the haystack in which you're searching, and how many characters are there actually in your alphabet. I don't know off the top of my head the trade-offs between those different parameters, and then you're starting to get into the weeds of, okay, which of these specific construction algorithms are going to give you the best real-world speed-ups for your situation.
Okay.
That's beyond what I can answer even taking a bit of time after class. That's let's sit down and try a bunch of these algorithms and figure it out for your given use case.
Sure.
Tim, you had one?
Which kind of illustrates your point about how it's about knowing the structure of the data in order to find the optimal solution, which leads into my question of if we were like, okay, so the original example that was given when we were starting string search was like genetic code, right? And of course, well, I'm not a biologist, but I assume that like because there's only 4 characters, you can essentially have like any combination of characters, right? Like they don't have like a limited number of words, like there are certain combinations of characters you will simply never see in like Moby Dick because they're not words, right? Yeah. So I guess my question is, because there is actually a severe constraint on what combinations of characters we can actually see, namely they have to be English words, why do we store a text file as characters rather than as numbers which identify words in a dictionary? Because not only, obviously that would be like more compressed, but I'm sure there's compression algorithms to deal with that. The reason I ask is if we are looking for a specific combination of words, shouldn't it be faster than using like all these advanced character by character pattern recognition rather than like if what we want is like a specific sequence of words like the shortcut to mushrooms, if we have 4 numbers that store 4 words, that should be faster to find than like checking all these characters individually. Like, is that a thing that would work, or is there reasons why that wouldn't work?
That is a thing that would work. Again, it's going to be kind of context dependent because in something like Microsoft Word, we actually want to allow for arbitrary pattern matching even for things that aren't words, and Google does the same thing. But in a scenario where you are guaranteed that the only types of searches permitted are for words, you can do all kinds of things. And yes, there is a nice link between compression algorithms and search that uses lookup tables. Outside the scope of the class, but a great thing to look into, and not a question I've ever had before. So yeah, really interesting idea.
Isn't a question, but just to add on with that, because I'm thinking a problem with that approach is because, sure, if you're searching just if you're searching within, say, a book or a corpus of text, then that the approach you suggested might work. But what if you're searching, say, YouTube usernames, for instance? Yeah. Which can be arbitrary, for example, XYZ, ZYZ, for instance, could be a username.
Yeah, so it only works in scenarios where the patterns are known to also be from a finite alphabet. You can also do things where if you are willing to apply restrictions on the pattern, then you can do all kinds of interesting things as well. One thing that's this is like an interesting, totally non-accessible aside, is that earlier in the history of computing, so the 1990s, particularly when people were doing video games development, consoles had really limited memory and processing power ability. And if you go even earlier, a lot of desktop computers had very severe limitations as well. And so you'll find if you go through the code that's been written for those very old video games, you'll often find developers do all these kinds of interesting hacks and clever things to come up with ways to get around the really limited memory and processing power availability on these older machines. Today, a lot of the tasks that we do are going to be performed so quickly on our computers for small amounts of data, like searching through a Microsoft Word document. It's not even worth it for the most part, over-engineering the search and over-engineering the search algorithms because the size of data that's in your average Word document pales in comparison with the speed of your processor, which is why for some of these examples that we're talking about, I like to think about things like Google or the Baillieu library, because that's where, at least on modern machines, we start running up against these limits. But there are a whole bunch of blogs that like go into the cool, interesting, weird, quirky things that old video game developers did. So recommend checking those out sometime in your free time. And with that, we will take a 6-minute break to get us back to 11:30. See you all in a couple of minutes. Welcome back, everyone. Lovely to see you're all still here after the break. In fact, we see a few new faces. Hopefully you've had a bit of a chance to go to the bathroom, have a snack. And now we return to our regular pop quiz format. Sorry, what was your name?
Angel, A-N-G-E.
Angel?
Yeah.
And how old are you? You can make it up if you don't want to answer the real answers to the questions.
Actually, I just had my birthdays like yesterday. So
Oh, you had your birthday yesterday?
So I'm 19. Yeah.
Can we sing happy birthday? Happy birthday to you. Happy birthday to you.
Oh my gosh.
Happy birthday, dear Angel. Happy birthday to you.
Thanks, guys. Thanks.
Probably a larger happy birthday than
Yeah.
Okay, so give us an age. It doesn't have to be your real age if you don't want to share.
100.
100?
Yeah.
Okay. And where are you from?
China.
That's a bit generic. Give us something more.
Southeast China.
Southeast China. Okay, great. And your name was Angel. Ooh, we lost something there. So let's say that we are putting you into the computer as a bunch of like these narrow data points. What would you do in C to store that information?
So store my name.
Yep.
My kind of like ID as an identity, and then my age, and then where am I from?
And what kinds of variables would you use to do that?
Variables, integer.
An integer for which of these?
Integer for age, string, and string for name and the cities that I'm from.
Yeah, and city would probably make sense to be a string as well. Yeah. Now, let's say that we are including, what was your name?
I'm Michael.
Michael. So let's say that we want Michael in our program as well. So now we've got a variable name 1 for Angel. We've got age 1, 100. And we have city 1 for southeastern China. Now, what do we do for Michael?
Name 2 for Michael.
Okay, so that's good. And we'll do all of those variables for Michael. And let's say, what was your name?
Daniel.
Daniel. Okay, so for Daniel, what do we do?
Name 3 for Daniel.
Okay, name 3 and age 3 for Daniel. And what was your name? Moen. Moen, what do we do for her?
Name 4 for Moen.
Okay, how many people are in this room? I'd say roughly 80 right now. So what are we going to write in C?
So 1 to 80, recording the name.
Okay, that seems like it's going to take a lot of time.
Yeah.
And then every time we want one of those variables, we'll have to explicitly type out. We've got a better tool for doing this. What's our current tool?
Current tool.
Yeah, like in C, what do we do when we have a collection of information right now?
Store it in an array.
An array. Okay, so now we've got one array for
name, one for age, and one for where we are from.
Okay, now let's say we start adding more information. So let's add your the year you enrolled at Melbourne Uni, and let's add your WAM, and let's add your favorite food, and let's add the names of any pets that you have. So now how many arrays do I have? Doesn't have to be exact.
5.
Yeah, 5 or 6. We've got too many. The more pieces of information I add about you, the more of these arrays we're going to have. And then every time, let's say I add a new student, I'm going to have to go into each of these. Let's say now we've got 20 different arrays for 20 different data points about you and modify each of them. So what do you think would be a better way of organizing this information? Let's forget about C for a second. What's a better way of organizing this?
Organizing it.
So rather than having this array and that 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 array, all of which have a different piece or type of information in it, what's a better way to arrange things?
I was thinking like in Python, we use dictionary to store different subjects.
So don't think about a computer for a minute.
Yeah.
Just generally, what's the right way to arrange this information?
Probably based on different people, like first split, because we have so much information. So for each people, like what's their pattern, what's their age. So like first their name, and then under it, just all their relevant information, and then the other people, and then the same.
Yeah, you've got it exactly right. So rather than storing the different categories of information together, each as an array, it makes more sense for us to talk about the idea of a person as a whole and store all the relevant details for each person together. And then we could have an array of?
Array of so many, like 5.
An array of?
Of one.
Of one category, and what would that category be?
Array of 80.
An array of people.
Array of people,
because we know we've now got this notion of a person that has all the relevant information about them. So what we really want is, instead of having an array for every type of possible information about a person, we want to have an array of people, and inside each of those people are all of the relevant data points from themselves. Thank you very much, Angel. Can we have a round of applause? And now we're going to compare these two methods in C. So this is the first version of my code, where I've done the first thing that Angel suggested, which was to have one array for every different piece of information about, instead of people, I'm doing with planets. So I have a type def for a string of maximum length 20 plus 1 for the null byte at the end, and I'm just going to call that a p stirred t, so I don't have to keep writing my type for a string of length 20 over and over and over. So I'm going to have a string array for the planet names. I'm going to have a string array for the name of the celestial body which they orbit. I'm going to have an array for the distance from the body that they're from the Earth. I'm going to have an array for their masses, and then I'm going to have an array for their radii. And what I'm going to allow people to do is I want to allow the user to type in the details for a planet and add it to my list of planets, or I want to be able to print the planets that I've got. And let's see how this works. So what I'm doing here is, for every planet that's in my planet index, which is going to, actually, let me start that again. For every planet up to the maximum number of planets, print the planet. And in this case, I have predefined that my array is just going to hold 2 planets. If you wanted to have a variable that allowed you to say, well, the array ends after 2 or ends after 3, you could do this as well. But this is just a simple example. So let's go back in here. And it works perfectly fine with 2 planets, nothing wrong with that. But we do have this issue that I now have to, every time that I want to add a new planet, I've got to go into each of these arrays and type it out. And also, every time I want to add a new attribute to a planet, I'm going to have to create a new array here. And this is going to start resulting in pretty messy code. So what I'm going to do instead is introduce a new tool in the C programming language that allows us to define a type that combines multiple different aspects of the same thing. And we're going to call these structs, just like structure. And so let's take a look at some code that I've written earlier that uses this new C keyword to enable this functionality. So let's open struct.c. And here I'm going to see the syntax for creating a struct. So one other thing you'll notice is I've combined my struct syntax with a type def to allow me to refer to my struct in shorthand just by planet_t. So this is the struct itself. And then I'm type defing this struct to planet t so that I can easily refer to that struct whenever I want. And inside my planet t, I'm going to have two strings, a distance, a mass, and a radius. And I can actually store collections of this struct. So I can store a lot of different planet t's within an array. So once I've defined this data type, then I can declare, I haven't done this here, have I? Let me see. No, I haven't done this here. Then I can declare an array later on that stores these. So we'll take a look at that later. So now I have used some special syntax available for struct initialization to create my two planets like I did before. So in this case, if you fill in the curly braces with elements that match the exact ordering and the exact number in the type definition, you can initialize it directly. So its name is the Earth, it orbits the Sun, its distance is 149.6 kilometers from the Sun, million kilometers from the Sun, sorry. Its mass is 5.9 times 10 to the 24 kilos, etc., etc. Now you'll also notice that I was able to declare the existence of another planet, but I haven't initialized it yet. Now, unlike pointers, as soon as you declare a struct like this, C sets aside the memory, but it hasn't put zeros in it. So it's whatever junk was in that area of memory before is now there, and so we actually have to, at some later point before using this, just like with other variables, we have to make sure that we've actually filled out all the different properties of the other planet. So we have to have filled out the name, the orbit's distance, mass, and radius, otherwise we might get invalid values. So in this case, I am creating a new planet inside my main function. I'm going to define a function copy struct, which we'll take a look at in a second, and then print the planet. And then we're also going to demonstrate using pointers to structs in a second. So the next thing we're going to look at is this print planet function. And in the print planet function, we can see how to access the different aspects or the different properties of a struct. So in this case, we're passing in a planet t, which is just the type we defined earlier. And I'm going to access the properties of it using this dot syntax. So here I'm accessing the name of whatever was in one planet with a dot. I'm going to access orbits with a dot, the distance with a dot, mass with a dot, and the radius with a dot. And you'll see here I've had to use the correct format specifiers for each of these types. So name is going to be a p string, which is just a string of length 20, and so I've used %s. Distance is what did I declare distance as a double? So I'm using a double format specifier. Same for mass, same for radius. Now let's take a look at copy struct. So copy struct is just going to read in from using scanf the values that I declare for a struct. So name and orbits are already strings, so we don't have the ampersand out the front. And these were integer values. So we are going to have to add the ampersand to pass in the address of those doubles so that scanf can correctly fill those in and return it to us. And then when this function is done, I'm just going to return the new planet. So let's look back up at our main function. Planet equals copy struct. So that's just a function that reads in from the user some values, puts it in the struct, and then returns that struct to the main function. We have print planet. And now let's look at pointer struct. So pointer struct is going to take in a pointer to a structure rather than the structure itself. This means that when you run the function, C is going to not copy in the entire structure, but just copy in the address of the structure. Then we can access the elements of the structure using the address of the structure. But there's some special syntax associated with this. Instead of using the dot, like we would have had before, if it's a pointer, we can not worry about the dereferencing and allow C to do it with some syntactic sugar. If we instead use a single dash and the greater than sign, we can automatically dereference and get the property simultaneously. So this is equivalent to syntactic sugar for the following. So if you write that, that's the same thing. Oh, sorry, if you write that, that's the same thing. I need to get my parentheses right. But it's a little confusing to remember to dereference the pointer and then access its property. So instead, what we're going to do is just, our compiler is going to give us this nice, easy syntax for accessing these properties. Now, you'll notice that here, because I am using scanf, scanf is already meant to take in a pointer, and so we could have just used the dot here. Okay, let's run this program. Enter name, orbits, distance, mass, radius. So Tim, orbits, FOA at a distance of 1.5. I think it's a bit awkward to type in a student's mass, so we're just going to leave that as a 1. And radius, what do you think your radius is? Let's put that as 250 kilometers. And then we can see Tim orbits FOA, his orbital distance is 1.5 million kilometers. His mass is 6.95 by 10 to the negative 310 kilos. That can't be right. And his radius is 6.95 by 10 to the negative 310. So this is what happens when we try and use human values for what should be planets, but you can see that the program does indeed work. And I'm just going to press Control-D and end that program, and you can play with it later. But this like fancy pointer syntax and the fact that we can do it both ways kind of raises the question of why would we bother with this? Does anyone have an idea of why we might really want to use pointers pretty substantially when using structs?
So I guess using structs would be way better because structs contains attributes and stuff, so like it's a better form of...
Well, why do we use pointers to structs frequently when we could just use structs themselves?
If we use pointers to structs, we know the index.
Well, we've got the address, but that doesn't, like, Ray doesn't care about the address of a given struct. Any other reason? So, I mean, we used to use pointers so that we could return multiple things from functions, but a struct can already store multiple things, so that reason doesn't work so well.
Because, hang on.
Go for it.
Yeah, because if we pass the whole struct as an argument, we would have to copy the entire struct to the function, and the struct might be very large.
Yeah, so remember that C, Gabriel, do you want to turn your microphone off? Thank you. So remember that C, when you pass an argument into a functional, you're actually getting the computer to copy what you passed into the memory space for that new function. And if our struct has a lot of different details about a person, so let's say instead of 5 attributes about a person, we had 200 attributes of a person, which actually seems pretty reasonable. I'd hope that all of you are interesting multidimensional humans, that this is going to start actually taxing our computer a lot. We're going to be spending a lot of our time doing this copying back and forth and less time actually interacting with the data. But instead, if all we're doing is modifying that same piece of data and like updating a person's details because you just tried a new flavor of donut and that's your new favorite food, it doesn't make sense to copy the whole thing, change that one element, and then copy it all back. Instead, we can just pass the address of the whole thing and modify that one element that we want. And in fact, a really nice place to see this in action is in the source code of the Linux kernel. Now, the Linux kernel is the core part of the operating system that actually drives the whole setup. And this is just one of the structs. I'm scrolling to get to this is all the different attributes of one specific part of the Linux kernel. This is the part of the Linux kernel. This is the struct that contains all the relevant information about one program that's running at one time. And I am going to keep talking because I'm still scrolling to get to the bottom of the struct. And we are going to spend the next minute or two of class time just listening to me yammer on until we get to the bottom of the task struct. Oh my God, it's still going. How many different things can you possibly need to know about one application? Oh, I'm running out of things to say. And there we go, finally. So that is an example of why we might not want to copy an entire struct into a function every time we want to use it, and why instead we are going to pass pointers to structs in many instances. Now, as pointers are one of the more complicated aspects of C programming, it is okay if while you're getting used to things that you're not necessarily coding optimally, particularly in your assignments. We're not going to penalize you for small faults like not quite optimizing the way you're passing structs around, but it is good to know, and particularly as you become more comfortable, to develop good programming habits around this kind of thing. So let's have, for example, our student struct, and I'm going to make this a student T. I'm going to leave off the definition for the time being. You can write it in your own time. And we're going to just remember that this arrow kind of symbol that we were using, which is a dash followed by a comparison sign, a greater than sign, is just going to be syntactic sugar for first dereferencing it and then getting the pointer. So let's recap our methods for creating the struct pointers. So method 1 is to create the struct first and then to create a pointer to the struct, just like we'd do with any other variable. So create the object first, get C to allocate the memory, initialize it, and then create a pointer to it by using the address of operator, which is that ampersand. Method 2 for creating a struct pointer. So now we can use this interesting new syntax that allows us to tell the computer that we actually want it to give us some memory. So rather than just having to create it manually ahead of time, we're going to use this new function called Malloc. Now, I will warn you that Malloc is one of the more challenging aspects of C programming to get right, along with pointers. The two kind of go hand in hand, and will start being the source of many of the unexplained bugs that you will have in your code. So a very frequent complaint I hear is, well, I ran my code on Ed, and then I run it on my own machine, and it works on one but doesn't work on the other. Typically, the reason that happens is because you've messed something up with pointers, arrays, or malloc, and I'll give us a little more on that in a little bit. So for the moment, let's just take as a given that malloc is going to allow us to ask the operating system to give us a chunk of memory. What that memory is going to be used for, how it will be used is up to us as the programmer, but what malloc does is just ask for that memory. And like any other function that's part of the C standard library, we could look up the man pages, which is a little complicated to read, or we could do what I often suggest, which is to go to the CS50 man pages, which are written in plain English and are a lot shorter, that can also give you a bit of a guide until you work your way up to reading the full man pages. So let's take a look at this syntax here. Malloc takes in one argument, and that's a size t variable. And a size t is a type def somewhere that your operating system has decided. What is the maximum amount? What is the maximum number that you can put in as an argument for the memory that you request? That doesn't mean that if you ask for a really big number, you'll get it, but size t determines the size of the number that you're allowed to ask for. So for example, on a 32-bit machine, you could have a size t actually being a 32-bit integer, because maybe the computer allows you to ask for 32 bits worth of memory, even if you're not actually even if it's not actually able to give it to you at a given time. So let's go back to our example code and see what we've asked for here. We've asked for the computer to Malloc to allocate for us memory equivalent to the size of a student t. And size of is a built-in keyword that interacts with the compiler that gets the compiler to tell us how large a given type is. Now, I'm going to warn you again, it generally functions to give us the size of the type, which means you can't just use it to figure out the size of a string or the size of an array. Remember, a string is typically a character pointer, and so if you ask for the size of a character pointer, you're going to get back what? The size of you get back the size of a pointer. So on a 32-bit machine, that would be 32 bits. On a 64-bit machine, that's probably 64 bits. So don't think that size of is going to be able to get you the size of anything. There are some edge cases where size of will return you the actual number of elements in the array, but highly recommend not doing things that way because that's an edge case that boils down to some interesting things about the way that array types are declared and does not give you a good understanding of how size of actually works. So returning to our line of code here, we are going to create a pointer to a student. We ask the operating system to allocate for us enough space for one student. And then what we're going to do is we're going to do an explicit cast and tell the computer that we plan to use this memory to point to a student. And so the reason we do this is so the compiler doesn't complain when we've taken what the man pages tells us is a void star pointer, which is just an arbitrary pointer to some memory, and attempted to assign it to a student pointer. So what we've done is we've asked the computer for memory equivalent to the size of a student t, and then what we've done is we've cast that to be equivalent to, with the address of that memory, we've cast that to a pointer for the student t type, and then assigned it to the student t. So what Malloc is giving us back is not actually the memory itself, because like, how do you give the memory itself to a function? What Malloc is doing is it's telling us the address of where the operating system has put that memory for us. And so we take that address and say, oh, right now it's a void star, which is an arbitrary address, and instead we're going to cast it to a student t pointer, which is a pointer to an address that, which is a pointer to a student t, which if we boil down to it, is an address in memory that is going to have enough space for a full student. And it was Ronald, right?
Hello?
Yeah.
Oh yeah, I have a question. Does the compiler automatically convert the student t pointer on the malloc?
The compiler will actually do it. I'm not sure what the most modern versions of the compiler do, what kind of warning they give. I know that at least in early compilers that I've taught with in previous versions of the class gives a warning and says mismatch types on both sides. I forget the exact message. A modern compiler might give you a slightly clearer message, but we can probably check that relatively quickly. Planet T star Ronald's planet equals malloc size of planet underscore t. GCC ronald.c. Whoops, Ronald. Oh, no warning. So looks like the latest version of GCC won't necessarily warn you right off the top. I still think it's probably good to do. There was a bit of a debate in the C community over whether it's better to have that explicit typecasting or not. I think at least at the stage at which you're at, it's probably better to do just as a reminder to yourself kind of what's going on. Do we have a microphone near Tim? You got one?
Yes. So I'm just trying to understand the syntax So I understand. So if we're looking at the line just below the function definition, where it starts with student T. So student T, okay, that's the type, right? Then you have star student, a student, which indicates that it is a student T pointer.
Yeah.
And the name that we've given that is a student. That's, understand that, equals in curve braces, in parentheses, student T space star, and then directly malloc. I've never seen this before, like where you have like brackets directly before a function being called. Why is this not a parameter to malloc? Like, what is this? Is this a typecasting?
It's just a typecast.
Okay, so
malloc returns a void star, and we want to convert that void star into a student T star.
Okay. So
It's just like putting int in there. If it was a function that normally returns float in there or double in there, and if it's a function that normally returns an int, it would convert it to a double. So this is returning a void star, and we are converting it to a student T star.
So what does malloc actually return? It returns a void star, which is just a memory address.
A memory address.
Then it's just giving that the type of a student T address, basically. Okay.
So we're saying this is not just any old pointer. It's actually a pointer to a student T.
Right. So we're rather than initializing an actual student, we're initializing a pointer, which we will eventually fill in with an actual student. But for now, it's just memory.
Yep, it's
that
just
has
memory.
no specific student attached to it until the next line where we start actually filling in that memory.
That's correct. One other thing that I want to emphasize is just because the operating system has allocated you memory doesn't mean that that memory has been zeroed or filled in with anything sensible. So if you were to start accessing, let's go to the Ronald example, and if I remove this line, let's say I comment that out, so we see a warning, Ronald planet distance is used uninitialized, and then if I run it, it's giving me 0, but that's kind of just random luck that distance happened to be 0 in that chunk of memory that the operating system gave me. It could just as easily be some other value. And I won't demo how badly that can go wrong now. But that gives us an indication of where there might be a bug on this slide. So we know that, I've told you that line 1 and line 2, like the void, the declaration of the function is fine. The next line is fine. Why is there a bug on the subsequent line that uses string copy? Switch.
I think it has something to do with deep copy when you use string copy.
Well, deep copy is really a Python concept, but you're kind of on the right track. What is a string in C?
A string is a special type array.
Yeah, it's a special type of array. And in order for us to copy something into the array, it has to exist, right?
Yep.
And an array is really just a chunk of memory. Have we created that array anywhere here?
I don't think so.
Well, it depends. So it depends how we have declared our student T, because we don't yet know if our student T already has space in a pre-declared array for the name, or if that's a pointer to the name. So let's look at 2 different ways that we could imagine declaring this for our planets. So you'll notice in this example, with our planets example, a p_t is declared as an array of length 20. And so inside our struct, we know that when this struct gets allocated, when we try and malloc that struct, and we try and take the size of, it's going to know that this is an array of size 20 plus 1, and that is an array of 20 plus 1 characters, and then it's going to set aside 64 bits for a double, 64 bits for a double, and 64 bits for a double. So this is actually going to work. If we were to malloc this and then try and string copy directly into name and orbits, it would work. However, we could also define pstring.t as a char star. Let me just remove that space. In which case, when we call malloc, malloc will create 2 pointers, each of which is going to be 64 bits, and then 64 bits for the distance, 64 bits for the mass, and 64 bits for the radius. And so if we immediately try string copying into name and orbits, those are pointers that haven't been initialized yet. And so what we might need to do is make further calls to malloc to set aside room for those strings themselves. And we'll get onto that with an example shortly. So up until now, all the variables that we have created have been where? Just say out. All the variables that have been created have been at the stack. So every time you create a new variable in a function, it gets added to the stack. Malloc behaves a bit differently. And the reason is because you can't rely on knowing how much a function is going to create. And functions get to decide when they use malloc when that memory gets created and when it gets destroyed. So what we're going to do is we're actually going to store it in a separate place in the heap down below. And the reason is once the function ends, if we've called malloc, we don't want that memory necessarily to be destroyed. We've told the computer to allocate memory for us. We're in control now. And so as you add elements to the heap is going to grow larger and larger and slowly and go in the opposite direction to the stack. So malloc allocates memory on the heap and is always going to return a pointer to the memory that's been allocated. And if you print out the actual number of the address, if you display what the address is of one of the variables you create via malloc versus one that you have just normally declared, if you take the address of an integer that you've declared normally, you'll actually see those addresses are really, really different because they come from different locations in the computer's memory layout. However, another trap with malloc is that because it's not cleaned up, the memory is that because the variables that you've created with malloc aren't automatically destroyed when the function ends, you have to manually tell the computer when you've done with them, when you're done with that variable, and then call free, which is the opposite. It tells the computer, okay, I don't need the memory anymore, you can now deallocate it. Now, one kind of trap is that telling the operating system that it can reclaim the memory is not the same as actually putting all zeros in that memory. The computer might decide, okay, that chunk of memory is there, I'll use it later and give it to some other program or some other part of the program when I need it. But there have been a number of instances, even in the last decade, where programmers have freed the memory for something that's meant to be secret, but have not written over it with zeros, and so later, there's a bug somewhere else in the program, and then someone can use that bug to read part of the heap, find a secret value that was stored in the heap and destroyed, meant to be temporary, and then use that to gain access to information that is meant to be secure. Had a question?
Well, you said what I was going to bring up.
Now, let's already talked about size of. So let's go back to our example, and now we're able to discuss all of the lines. So we have string copy, which is a function in the C standard library that hopefully you've seen by now. Have you seen string copy? Yes. Copies from the source to the destination, so copies Kwaku into student name and location. Tanzania copies that into, and we can also set the student age using our pointer syntax. And then we can print student name, which just prints the name. And then at the end of all of this, remember to free. Now this can start getting a little difficult when you are freeing the memory in a different function to the one in which you've used it. And you have to start keeping track of, okay, which memory have I allocated, where have I allocated it, and what is the right time to free it? And this is often one of the big traps in C programming and in programming in closely related languages. And in fact, have you ever had that issue where you have like too many tabs open on Google Chrome and the whole computer starts slowing down, and then even when you close some tabs, the computer is still slow? Ever happened to anyone? Yeah, a few people in the room. Yeah, I see a few hands. What is likely happening there is something called a memory leak. And that is where the author of some program has forgotten to free some of the memory that they've used up. And what that means is the more you use the program, until the program ends, it keeps allocating more memory, but some of the memory is leaking because it's never freed. And so you've used Chrome for a week, you've opened a whole bunch of tabs, you've closed a whole bunch of tabs, but closing the tabs, the developer has forgotten to add a free, and so some of the memory from it is still allocated. Even though it's not being used at all, the operating system is still being requested to have it. And so over time, this builds up, and now you're using more memory than your computer actually has in RAM, and so your computer starts doing something called swapping. And this is where it takes some of the items that are in RAM, puts them on the hard drive, and then frees up some more space in RAM, but then later on, when you need some of the stuff that it's put on the hard drive, it has to bring it back. And if you're using way too much memory, this process is going to happen over and over and over. And what do we know about hard drives compared to RAM? They're really, really slow, like on a couple of orders of magnitude slower. And so then you can get a couple of orders of magnitude slowdown on your computer because every time it wants to do an operation, it has to swap some memory out of its RAM and onto the hard disk. And so the things that you are learning today are the source of actual real problems in real life production code. Any questions on this so far? Go ahead.
Comment.
Yeah.
And this is also the source of many criticisms of C that you will inevitably find online.
And that is true. This is one reason why many people prefer using other languages than C. And you might ask then, why does anyone use C? Well, one reason why one might use C is that there are many devices that only really support C compilers and for which compilers in other languages haven't been written, or where control over these low-level details is important. So if you are, say, writing the software that controls the chip inside a hard drive, for the most part, that kind of thing is going to be written in C. Or the code that controls a smart home light bulb, also probably going to be written in C, because those devices require fairly exquisite control over low-level details, and having something that's constantly figuring out, okay, he's allocated memory here and she's allocated memory there, and when that's done, I need to clean those both up. That takes processing power that those devices might not have. And it was Sam. Sorry, Sam.
Thanks. So if you had a memory leak, would the way to fix that just be like resetting your computer and just clearing the RAM?
Yeah, so if it's really bad, you might need to reset the computer. In most cases, you can typically just close the application. And when an application is closed, under regular circumstances, the operating system has the right to reclaim any memory that it was allocated. There are ways for programs to allocate memory which the operating system is instructed not to clean up, even after the program closes. And if you've got a memory leak there, then you can run into serious problems. The other thing that modern operating systems often have is an out-of-memory killer. So what that means is when a program is using way in excess of the amount of memory that it's meant to be using, the operating system will terminate it.
Right.
And that's configurable, at least on Linux.
Cool, thank you.
Any more questions on this one? So let's go back for a second. Here. Okay. So let's say you're having a busy day. You've allocated a bunch of items on the stack, and now you've allocated a lot of memory on the heap. What could go wrong? And Sam, you've got the microphone.
Could the stack and the heap both get so big that they kind of meet each other and you can't really add, or like you try and add something to the heap, but it goes to the kind of the top of the stack, or you add something to the stack and it goes to the top of the heap?
And what are two things that could possibly happen at this point?
Either it doesn't work, or like the data gets overwritten and then you have a problem of some kind?
So I guess there are kind of three things that could happen. If we're running on a real old school operating system that is not paying attention, then it might just overwrite stuff. If you're running on a well-designed operating system, what will the operating system probably do?
Segfault?
Segfault. And number 3, if you've just called Malloc, but there's not enough room to Malloc, the operating system, you've asked it to Malloc a lot of memory, and there's not enough room for it to allocate it. What might the operating system choose to do? Return null. Yeah, the operating system might choose to return null from Malloc, and additionally set an error value. So you may not have seen this yet, but a lot of the C standard library functions, on top of just providing a return value, can also set an error code that you can later access. And I'm not sure if you've seen that. Have you guys seen that yet with John, Jong, or Sasha? If not, we'll go over it shortly. So let's actually look at a demo of what happens when we try and allocate too much memory. So here is my function malloc.c. I'm going to have an array of pointers, and we'll start with allocating 10 bytes. And then for each iteration of this loop, I'm going to multiply by 10,000 bytes. So trying to allocate successively larger and larger chunks of memory, and let's see what the computer does. And then at the end, I'm going to free all of those. So we were able to allocate 10 bytes, we were able to allocate 10,000 bytes, we were able to allocate that many bytes, and now we're getting to more decimal places than I can count quickly. But when we tried to do our last 2, Malloc actually failed. So along with this failed, there is actually a function inside the C standard library called p-error, which allows us to print the error message that a standard library function failed would have given us had it been able to print something directly for us. So let's just write that. Now, do not try and run p-error if an error hasn't occurred yet. So what you first need to do is you need to check the return value of a given function. If the return value indicates that an error occurred, then there is behind the scenes a global variable called errornum that will be set. And then p-error has a lookup table that it can use to look up what that error number what error message that corresponds to for the last function you just tried to run. So you can get it to actually write it to a string instead of to standard out. Let's try there. There we go, and now we can see the error message that Malloc was actually giving us. So we can see the reason why Malloc failed, and in this case it was generic, cannot allocate memory. But for a variety of standard library functions, you may actually get something more informative that could help you debug your program. Now, one other kind of weird quirk is that Malloc can actually return successfully even if it's allocating more memory than your computer physically has. Now, this is a little mysterious until we take a look back at our picture over here. Now, you'll see that, at least in this example, on a 32-bit machine, my addresses are running all the way from 0x000 all the way to FFFFFF. That's the full 32 bits, even though a given computer, like an old computer, might only have 1 gigabyte of RAM, even though this allows us, in theory, for 4 gigabytes of RAM, and we're creating a memory mapping, this like map, is using all 4 gigabytes of possible addresses. Now, what's actually happening behind the scenes is the computer is using something called virtual memory. So it is figuring out, okay, which chunks of this memory are actually used, and behind the scenes, the operating system is mapping the chunks that are actually used to the real locations on the actual memory chips inside the computer. So as long as you're not actually using more chunks than your physical memory has available, the computer will allow you to write to those chunks. And in fact, oftentimes, because the operating system is intelligent, it will even allow you to allocate more chunks than physical memory that your computer has, because you might be configured to do this swapping thing, where when you run out of physical chunks in your computer's memory, it writes some of those out to your hard drive. So the main reason why we have this system is so if we're using a 32-bit machine, that we can still use all 4 gigabytes of memory to arrange our program, even if the actual memory available on our computer is smaller, and this gives us a lot of flexibility. In fact, a little bit of swapping is okay. We just don't want to get to the point where the computer is doing what we call thrashing and doing this swapping in and out over and over and over and over and over. And so this is a very powerful technique that if you stay in the major, you will learn about in the computer systems class. I think it's actually kind of fun and kind of cool, and it allows our computers to be much more powerful than they would be otherwise with what you necessarily might be able to afford just in terms of putting the RAM in. And we are back for our last little segment of the day where we're just going to talk a little bit more about structs. So one other quite powerful thing that you can do with structs is have structs within structs. And if you really want, you can have structs within structs within structs. But this starts to get to the point where, as we saw before, you've created these very unwieldy objects that now are very difficult to manage in memory, and that if you were to pass as an argument to a function, would result in a very large copy. So here we can see one example in the Linux kernel inside the task struct that we scrolled through earlier of exactly this happening. So the very first thing inside the task struct, which remember refers to an application running on your computer, or loosely, is we have a substruct within it called struct thread info. Now instead of embedding a whole struct within the larger struct, we could also use a... What do we do when we don't want to pass around a whole struct? We could use a pointer. So in theory, we could have made this a struct star thread info. The specific reasons why you might choose to do one or another in a specific context often depends on the size and the context of using them, but it's just a useful trick to know. So now if we look at the thread info struct, we can see it's much smaller, and this has actually been the struct that we have embedded within the other one. But you do have to make sure to get your ordering and your type defs right, such that you don't refer to a substruct before inside the parent struct before you've actually declared it. And so one way of getting around this is with what we call forward declarations. So you've seen forward declarations of functions. This is where you have the prototype at the top, but you actually define the substance of it after. And you can do the same thing with type defs for structs, where you provide the actual definition of the struct later, but you provide the type def earlier. And there are a variety of techniques to do this that we'll see throughout the semester. Okay, now let's go back to a code demo just to show you a simple nested struct and where we might use this. So here I've actually finally created my student T. So I've given it a number of different properties. I have the full name of the student, student number, date of birth, number of subjects, and then inside it, I've actually allocated for each student an array that can contain subject T's, and these subject T's are in an array up to max number of subjects. So I've actually pre-allocated this. So if I look above, I can see max subjects is 8. So each student already comes with space allocated for 8 subject T's. Now, if I look up, I can see subject T, it's a subject code, a final mark, and assessment scores for each of the assessments. And this is 10 assessments per subject maximum, and then a variable that keeps track of how many assessments are actually being used for that assessment. Now, what this means is that I'm going to have layers of abstraction here. I have my parent struct that within it has an array of subjects, and each of those subjects within it has an array of assessment scores. And so actually figuring out exactly how the memory is going to be allocated gets complicated. And this is even before factoring in the fact that sometimes the compiler will add extra space in between things so that they run efficiently on the actual hardware design. And if you want more on that, we can talk about it outside of class. But for our purposes, it's sufficient just to know that this code is going to work. And now we can start manipulating them. So we can, for example, print all of the base aspects of the student that we have here. And then for each of the subjects that a student has created, that a student has allocated themselves to. So we can see we have a variable that tells us how many subjects inside the subjects array are actually allocated. So for each of those subjects within that student, we can go in and print the subject code and print the final mark. And this should probably be on a new line if I'm keeping to good style. So now this code is starting to look complicated, even though the ideas behind it are still conceptually quite simple. Microphone for Tim. Thank you, Sam.
So coming from people who did FOC or Python, this seems very analogous to classes, except that there's no methods. So for example, you have this function print student. In Python, we define a student class, and we might have classes defined to be connected to that class, but we would then, within the class definition, have a method print. Whereas this, what we're doing is creating our own function, but crucially, the input is of type student T.
Yeah, so that is correct. They are very similar to Python objects or Python classes, with the exception that the methods are external. Now, if you want to be really sneaky, there are ways in C to actually implement something that looks very similar to classes in Python. But the way you would do this is a little more complicated and relies on some concepts that we'll only get to in 2 or 3 weeks. But when we get to that point, you can remind me, and I can make another offhand remark about how we might accomplish that.
So I guess my question is, why does C not have classes? And what is the benefit or what is the functional difference between those two approaches?
So classes are really kind of syntactic sugar. You could embed within a struct, for example. We could have, we haven't gotten to this yet, which makes it a little tricky to describe, but you can have pointers to functions inside the struct, and the pointers could be, okay, this is a pointer to the way you print this struct. This is a pointer to the way you copy this struct, etc. And that's essentially the same as having methods. Why doesn't C have that built in? One of the big ideas behind C when it was created was that it should replicate as closely as possible the way that the computer is functioning under the hood. Structs were seen as an appropriate way of just helping you organize memory, but classes were seen as having too much abstraction away from the low-level machine details. Further to that, I don't remember. We can look this up very quickly, which why not? And this goes back to a little discussion about Barbara Liskov at the top. C was created in 1978, thereabouts, and was closely related to other programming languages from the time. And I don't know, oriented programming. Let's see. Yeah, and object-oriented programming was kind of, while it existed in some sense in the 60s, and there had been even some conceptual elements of it that arose in the 1950s, it didn't really become a common paradigm until the late 1970s. And so kind of what was happening, C was developing on one track conceptually, and object-oriented programming was happening on another track conceptually. And so the fundamental philosophy of C didn't interact with the object-oriented philosophy early enough. So it may partially be a historical accident, even while I think there are still good justifications why it doesn't fit naturally within the C philosophy. So some of the stuff around programming languages is a matter of history rather than around pure design. Okay, where were we? Oh, we were at our subjects demo. Okay, so now I've done a, let's swap out Jessica for Jessie, because we have met a Jessie today. And we're not going to use realistic details, but let's make your last name Vanderbilt for today. How does that sound? And so I'm going to create a student T array of all the students in FOA. Let's say there are 500 of you, just as a rough approximation. And then I can create individual student Ts and start to put them in the array. So I'm going to add a date of birth, which is a date T. And if I look at a date T, I've declared it above here as 3 different integers, a year integer, a month integer, and a day integer. And so I've used the struct. One other way of doing struct syntax is just like this. So I've created a struct 1912 and 2003. And then C is going to automatically allow me to do assignment as long as it happens during initialization. So I can't just arbitrarily assign one struct to another struct, but during the initialization process, the compiler allows me this syntactic sugar. And then I can also fill in his full name, number of subjects, put in a student number, and then also put in some subjects. So Comp 101 got an 89 overall. Should we make that a 99? What do you guys think? 99? Yeah, absolutely. 99? And then we have the individual assessment scores, and then 3 different assessments, whereas for 102, we had 4 assessments and didn't go quite as well. Let's make that a 99 as well. I think that's more representative of your character as a student. Actually, 98. 98 okay? Not good enough. Still an H1. So then what we're going to do is we are going to try and assign that student to the array and increase the number of active students. Then we're going to do the same with, we don't have a Kathleen, but so we're going to swap out Kathleen for Alex. I don't know which of the Alexes this is, but be at least one of the Alexes. And do the same kind of thing, and then we can iterate through the active student array. So let's nested. And then we can see, using our fairly deeply nested objects, our structs, we can store all of this information in a way that is much, much easier to access and process. And that is really why we're using structs. The syntactic sugar is nice over arrays, but more it allows us to organize our data in a way that is reasonable and to create these kind of complex types that represent things that we might actually use. So now back to some pros and cons of using structs. So there are some really helpful things about them. They make bookkeeping much easier. We don't have to keep track of an array index, which we use across multiple different arrays. It's kind of flexible. We can easily, in our code, add another attribute to our struct quite easily. We can use a struct to potentially return multiple items, multiple sub-items from a function by having a struct that contains all those sub-items and just returning that. And the syntax is nice and easy, so it makes it easy for us to maintain code and build in hierarchies. However, there are some limitations, and in particular, these arise from comparing structs. Because, what does it mean to compare two people? I mean, you could compare two people based on their ages, you could compare them based on the order of their alphabet in which their first name appears. So it doesn't necessarily make sense to say, well, is student TA bigger than student TB? Whereas with items in an array, we can often more directly do that. As long as they're not strings, then we'd have to use string compare. So this means you can't use the syntax, are these two structs equivalent to each other? Because just the same way as comparison is not easy to define, equivalence is not easy to define. It might be that if two people have an identical student number, they're the same. Or if two people share the same name, or if two people share all the attributes. And so you have to write your own code if you want to implement these kinds of attributes. So you might ask, okay, so that's enough rambling about it. How are they actually different from arrays? What are the operations I can do and what are the operations I can't do? And so I've prepared for all of you a table that you can get in the slides and that's also available in the book slides that gives you more or less an overview of how they compare to arrays and some of their similarities and differences syntactically in C. So what structs have allowed for us is a new level of abstraction, a new way to represent data that's not just using the basic types. This is very similar to another type of abstraction that we actually did quite recently, where we developed an abstraction over execution. So rather than just having a single function and using loops and control statements all within the main function, we used the notion of defining our own functions as a way to abstract out components of execution into nice discrete pieces. Structs enable us to do a similar thing for data. And this is one of the key themes of the class, is that abstraction not only allows us to write code more flexibly, but also allows us to think about things in slightly different ways, and enables us powerful things like new algorithms that we can actually use as a result of having imposed structure onto our data, whether that's through a suffix array or through a regular array or through our own custom types. Each of these are going to enable us to process our data in slightly different ways. Now, you can do this without any of the syntactic sugar that the compiler affords. If the compiler didn't give us syntax for arrays, but made us use memory addresses directly and made us do calculations on memory addresses, we could still write the same algorithms. But it would be much, much more work because we'd have to essentially do the same thing as we're doing using our fancy array syntax and then our abstraction on that, the suffix array, but would have to do it using the syntax of raw memory, which would make it much, much harder. So it's very sensible to see and clear to see why we might have developed this method of abstraction. So a few more things on Malloc. Here is a sample outline of a well-designed program that uses Malloc. So the basic structure is first create a pointer to the type that you're going to want to point to. Next, set that pointer to the outcome of Malloc. Next, check that Malloc actually succeeded by making sure that pointer is not null. If that pointer is null, printf that there was an error or use p-error and then exit, because if Malloc fails, that means that something is really wrong with your program. There are other functions that might be less of an issue if they fail, but if Malloc fails, that indicates something is deeply wrong and you probably don't want to continue. Then you might want to assert that the pointer is actually valid, and then you can actually do stuff with the pointer before eventually freeing it. Then, once you've freed it, there's this little trap at the end. What have I done at the very, very end? What have I done at the end? Now, I've set my pointer to null. And this is because just telling the operating system that I'm giving it back memory is not the same as setting the variable that contained a numeric value that was an address to 0. You can set a pointer variable to have an address. That doesn't mean that memory is yours. You can write in memory address 5475 into a pointer. That doesn't mean that if you use that pointer, you'll be successful, but there's nothing that the compiler will do to stop you from manually writing that address in. Just the same, when you've finished using the pointer, you both have to tell the operating system that you're giving it the memory back and also set the pointer to null to let yourself know that that pointer is now invalid and that memory you shouldn't use. What happens if you try and keep that address around? Well, you might accidentally end up either trying to use that pointer, dereferencing it when that memory address is no longer yours, in which case you might get a segfault, you might get a random value, or you might try and free it a second time. And both of these types of actions could enable someone to manipulate the computer by using memory that might be allocated to them, even though you think it's allocated to you because you haven't adequately kept track of the fact that you actually previously freed that memory. So that's another way that vulnerabilities can go into programs. Okay, so let's go to another example with a structure and some memory that we've allocated. Now we've got our plain T. The exact specifics of our plain T don't matter for the minute, but let's make this a Boeing 747. It's a Qantas one, 174 seats. And I'm going to allocate space for a bunch of seat Ts on this plane. But now there comes an announcement, attention passengers, due to pilot availability, we're going to have to change your gate to accommodate a larger plane. So there's now going to be a new plane. And the new plane is going to have 246 seats. But previously, we Malloc'd enough room on our previous slide here. We only Malloc'd enough room for 174 seats. So what are we going to do? So one option to transfer the passenger data onto the new plane data structure would be to use the memory at the end of the 174 seats. So we allocated space for 174 seats. Let's just use seat 245. What do you guys think will happen if I try and use seat 245 when I've only allocated space for 178? Just say it out loud. Segfault. Okay, probably not a good idea. Also, a bunch of you are cheating because you've got my presentation slides ahead of time. It's very unfair. I can't surprise you. Maybe I should take the answers out next time. Okay, so we have option 1, which is to do a manual copy, go seat by seat through the old seats, Malloc space for a new seat array. Let me reverse that. Malloc space for 245 seats, or however many seats are on the new plane, and then one by one go through every seat on the previous array that we allocated and copy it in. So it would look something like this, assuming that we have a function copy seat that we've written. So for as many seats as were on the old seat, on the old plane, so I have new plane and plane, which was just the old plane, run copy seat on the old seat, and then copy the data onto new seat, and then free the old seat array. Why might this not be our number one option? Who's got microphones? Hands up if you've got a microphone.
It's slow, and it's like also creating a new memory space that you need to use.
Yeah, so it seems to make sense that we want something kind of in between technique 0, where we just use the memory that wasn't allocated to us at the end there, and this option where we're really allocating a whole large second chunk and then copying everything over one by one. What we really want is to tell the operating system, like, hey, if there's extra space at the old one, or you figure out what's best, give us enough space for the new memory, ideally with a minimum of copying, and just copy everything over. And we have a function that actually does instruct the operating system to do this, to handle those details. You know, if there's extra memory at the end, just extend it. Otherwise, give me a new chunk and copy everything over as efficiently as possible. And this is the realloc function. And so what we can do here is instead, we just run the realloc function with the new number of seats that we need. So the first argument is going to be a pointer to the object that we want resized. It should be an object that we created using Malloc. It can't just be any random array because it has to be something on the heap. And then the second argument is going to be the new size that you want for it. So this leads us to the last question for the day, which is how much space should we generally allocate? Yifeng, do you want to answer that for us? So if I need more space, how much space should I add?
Add additional space.
So one answer is just add the exact additional amount of space you need. So let's say I had room for 500 students in FOA and we were full up and we had another student come. What would your answer tell us to do?
Add 1.
Add 1. Now, what if we know we're before the census date? What's probably going to be happening in our class? Before the census date, the date in which everyone has to decide what classes they're taking.
Oh, then do you mean there's no additional students?
Well, we're probably going to have a lot of students joining and leaving. And so this would mean that we'd be calling realloc a bunch of times. And depending on exactly how lucky we got with how much memory was available, this means we'd be running this expensive operation over and over again. We'd be asking the operating system to constantly find chunks of memory for us. So in most cases, it's not going to make sense to just allocate memory exactly for the amount we need. Now, who remembers something about computer architecture that might tell us what a good number to pick for growing our allocations might be? So it was Aaron? Danny, sorry.
It works by powers of
Works by powers of 2. Sorry, Danny, we'll get that for next time. Works by powers of 2. So generally, a good option is going to be to double the amount of space that you have allocated in many instances. Now, this is a rule of thumb. It's not always true, particularly if you're using a very large amount of memory. Doubling your very large amount of memory might not be such a wise choice, but in general, this can help preserve some efficiencies. And this is because Realloc is quite expensive, and so it's often better to waste a little bit of memory rather than waste a lot of time. With that, I think we are just about ready to finish up. The only thing is, I have suddenly introduced a whole lot of complexity into our programming. I've given you all these instructions, detailed instructions, for how you should manage your memory to make sure that you don't go off rails, to make sure that you don't get vulnerabilities, to make sure that you don't get memory leaks. And you're probably wondering, or if you're not, you should be, how on earth am I going to do this without messing up? And in fact, you'll find when you're writing your assignment 2 that is going to require memory management, you will get bugs and you will die. Well, hopefully not the latter part, but at least you will struggle with memory errors. And so what we're going to do in the next class is we're going to start talking both about ways to help you as a developer spot these errors using a bunch of different tooling. And then we're going to look at a new data structure that this Malloc tool has actually enabled us to create to justify why it is worth going through all this extra effort of manually managing our memory in the first place. So with that, thank you very much. Have a really wonderful break, and I will see you in 2 weeks.